Hi, in this video, I'm going to present our EMC squared efficient MCMC negative sampling for contrastive learning with global convergence. This is a joint work with Professor Wai from Chinese University of Hong Kong, Params Rowan and Somayati from Amazon AWS, and Professor Hong from University of Minnesota. In contrastive learning, our objective is to find feature encoders that the encodings maximizes the similarity between positive data pairs and minimizes similarity of negative pairs. One famous example is the CLIP paper from ICML 2021, where using one contrastive learning loss objective, they're able to train an image encoder and test encoder at the same time. In contrastive learning, we are interested into looking into these two loss functions. The first loss function is called the info-NC loss, where in the denominator, the negative scores are summed over a mini batch samples of size B. On the other hand, we have a global contrastive loss, where the denominator is summed over all the negative samples of the data point X, and it turns out that the global contrastive loss is the limiting upper bound of the info-NC loss as the batch size of info-NC loss increases up to the size of the whole negative data set. In our paper, we propose to minimize the global contrastive loss, which is the upper bound, and upper bound is for any batch size that is used in CLIP at the cost of only a constant batch size using MCMC sampling. So in order to understand the algorithm, we calculate the gradient of the global loss objective, and it composes of two parts. The first part is the positive pair gradient, and the second part corresponds to the negative pair gradient. And in particular, the negative pair gradient actually follows a softmax distribution with probability distributions defined according to this equation. And what it says is that as long as we can sample the negative gradient according to the softmax distribution, then we have an accurate gradient estimate of the global loss. So in our paper, our method is to apply the Metropolis-Hastings algorithm to sample the negative loss gradient. So according to the Metropolis-Hastings algorithm, what we need to do is to accept new negative samples with probability that is equal to the ratio of the exponential score. And in the algorithm, we need to store what is the previous negative samples. We also call it the Markov chain state. And it turns out that such an acceptance rejection procedure is similar to what other papers has been doing as called hardness-aware negative sampling, because the more similar our new negative sample is, the higher chance it is that it will be accepted as our new negative sample. To run our algorithms, there are two overheads due to sampling. The first is a computational overhead, where we need to compute the acceptance probability for each new negative samples that we consider. The second overhead is on the memory, where we need to store the exponential scores of the previously accepted negative sample for every for every data point in our data set. Our algorithm works by warm starting, meaning that at every epoch, we retain the Markov chain state from the previous epoch, and we only use a constant amount of samples to run the Markov chain, which is more efficient than as if you were restarting or cold starting the Markov chain at every epoch. In our paper, we showed the analysis that our algorithm would converge at the rate of 1 over square root t. For the experiments, we showed that our algorithms have shown a competitive small batch performance compared to the state-of-the-art algorithms. And in particular, we also run another set of algorithms where to the extreme small batch size of 4, our algorithm converges accurately to the stationary solution. Thank you for your attention, and here are the links to our paper and to our open source code.